Hello, this is the intro to section 1.4 lesson. In section 1.4 there are kind of two big topics. The first is the axioms of probability. In this introductory lesson we're going to discuss these axioms and a little bit of background material to help us better understand them. So whenever we talk about probability, there's one name that we should always mention, and that's Andrei Kolmogorov. Here's a picture of him. He was a 20th century Russian mathematician who worked in a lot of different fields, but he's probably best known for his work in probability. And that's because Andrei Kolmogorov devised our current set of axioms of probability that we use to study probability. So this phrase, axioms of probability, maybe raises two questions. The first is, what do we mean by an axiom? Well, let's define an axiom. An axiom is a property that is regarded as being established, accepted, or self-evidently true. So in other words, an axiom is a simple property that we're going to accept as being true without any proof. And so axioms of probability are going to be a set of simple properties of probability that we're going to accept without any sort of proof. The second question that this phrase axioms of probability raises is, so what? Who cares? What are we going to do with them? Well, let's kind of review the basic method for how mathematics works. Mathematics uses this so-called axiomatic system, or maybe axiomatic method. And in this system, our foundation is formed by axioms and definitions. So definitions, we know what definitions are. Axioms are these self-evident properties. And so we're going to start off with those and combine them with maybe the rules of logic to prove some simple results that we might call propositions or theorems. And then we can take those simple results, combine them with axioms, definitions, and logic to get more complex results that we call theorems. And so in this section we're going to start doing this axiomatic system with probability. We're going to talk about some definitions. We're going to state our axioms. We're going to use those to prove some simple results. And then as we go through the semester, we'll use these simple results to prove more complex results about probability. Okay? So this is how we're going to use these axioms that we state here in this section. Okay. Now, next thing I want to do before we get into our axioms of probability, we want to review some things. First of all, we're going to review some definitions from earlier in this chapter. Second, we're going to review some basic ideas from set theory and some simple pictures we can draw with sets called Venn diagrams. And then we're also going to review the idea of functions from Calculus 1. Okay. So first of all, our definitions. Here's a couple definitions that we've defined earlier on. First of all, the sample space is the set of all possible outcomes of some sort of random experiment. So remember, a random experiment is something that we don't know what's going to happen until we actually do it. An outcome is the result of a random experiment. Sample space is the set of all possible outcomes. Now, an event is a set of outcomes, or stated another way, it's a subset of the sample space. Now, one reason I review these definitions is to stress the fact that sets are an important part of probability. We're going to use a lot of set ideas to prove properties of probability. Okay. Now let's talk about a little simple picture that we can use to illustrate some of these ideas. So this rectangle here labeled S, that's our sample space. That's the set of all possible outcomes. Now this circle here labeled A, that's maybe one event. That's a subset of the sample space. It's a set of outcomes. Here's another event, call it B. It's another set of outcomes or another subset of the sample space. Maybe sets A and B overlap like this, maybe they don't overlap. There's lots of different ways we could draw this picture. But here's a simple Venn diagram that illustrates our set of our sample space and then two different events inside of that sample space. Okay. Now let's review some basic ideas from set theory. Well, first idea is the union, denoted A and then union B. and that is defined to be the set of everything that's in set A or set B. Second idea is the intersection, denoted A intersect B, and that's the set of everything in set A and in set B. So remember from basic set theory, this union symbol is synonymous with the word or, intersection symbol is synonymous with the word and. And keep that in mind as we talk more about probability. So let's draw some simple Venn diagrams to illustrate these ideas. So again, here's our sample space, here's a set A, here's a set B. A union B is the set of everything that's in A or in B, or maybe it can be in both sets A and B. So this shaded region here is the set A union B. Now here's the A intersect B, this is the set of everything that's in A and B. So that's going to be just this center little wedge here. And so there we go. There's some simple Venn diagrams of unions and intersections. Okay. A couple more ideas from set theory. Subset, denoted A is a subset of B, and that symbol means that everything in set A is also in set B. Another idea is the complement, denoted A with a bar over the top, or sometimes it's denoted A with a little prime next to it. Complement is the opposite of a set A. It's everything that's not in set A. So to illustrate these ideas with a Venn diagram, again, here's our sample space. Here's maybe a set B, and then inside of that set is a smaller set, call it A. And so here everything in A is also in B, and so A is a subset of B. In this picture, here's our sample space. Here's our set A, and then this shaded region is everything that's not in A. So that shaded region is our complement. Next idea is the empty set. Looks like this is denoted with this symbol, which looks kind of like a 0. And the empty set is a set with no elements. Next idea is the idea of disjoint. If A intersect B equals the empty set, then A and B are said to be disjoint. So if we draw a simple picture of this, again, here's our sample space, here's a set A, an event A, here's another event B, and notice how those two sets don't overlap. So there is nothing that is in both A and B, so A intersect B equals the empty set. So that means that those two sets are disjoint. So hopefully these ideas from set theory all look familiar. Keep these in mind as we read through section 1.4. All right, the next idea is the idea of functions. And we talked about functions since probably middle school or earlier. Functions are, from kind of some perspective, very simple, and other perspectives maybe a little more complex. When we think about a function, we often think about something that looks like this. F of x equals 2x plus 3. F is the name of the function, x is the name of the input. The right-hand side describes what we do with that input. Okay? So now what do we do with functions? Well, we often input numbers and we get out outputs. So for instance, we input the number 4, we take that times 2 to get 8, we add 3, and we get the number 11. So this input 4 is associated with this output 11. Likewise, if we put in a -5, do the arithmetic to it, we get out the number -7. So this input is associated with this output -7. And so here's a table of some possible different inputs and their associated outputs. A simple illustration we use to illustrate this idea of a function is we can sometimes think of a function as a machine. A function takes in an input, call it x. Function does something to that input, and then it outputs some output, call it f of x. A little simpler picture of this is a function takes in some sort of input, does something to that input, and spits out an output. So the big point here is that a function is all about inputs and outputs. We put in something, we get out something. So this leads to kind of an informal definition of a function. A function is a rule that takes in some input and returns some sort of output. Now those inputs could be anything. They don't have to be numbers, and likewise those outputs don't have to be numbers. In Calculus 1, the inputs and the outputs were usually numbers, but that's not always the case. Now, my favorite example of a function that doesn't involve numbers is a stoplight. Right? You get up to a stoplight and you see three colors, either red, green, or yellow. Now, each one of those colors is associated with an action. Right? If you see a red light, you stop. If you see a green light, you go. If you see a yellow light, well, you speed up or do something like that. So the point here is that in this idea of a stoplight, we have associated each color with an action. So it's all about inputs and outputs. Doesn't have anything to do with numbers or arithmetic, but a stoplight is a function. So again, function is all about inputs and outputs. Now, what does this have to do with probability? Well, let's kind of review an example from earlier on this semester, example 122. In this example, we dealt with a random experiment of choosing a family with 2 children. That's a random experiment because we don't know what kind of family we're going to get till we actually choose them. Now, in this example, we dealt with a couple of different events. Let's let A be the event that the family has at least one boy. And then B is the event that a family has exactly one boy and one girl. Now, we could describe both of those events as a set of outcomes. We're not going to do that here. You can go back and review this example if you want. But now, in that example, we calculated the probabilities of these 2 events. The probability of A was 0.75, and the probability of B is 0.5. Now, we're not going to do that here. That's not really the point. What I want you to realize is that this idea of probability, probability took in this event A and returned a number. Likewise, this idea of probability took in a different event B and returned a different number. And so in this idea of probability, we have inputs and we have outputs. And so in other words, probability is a function. This idea of probability is a function. It takes in an event and returns a number. And so it's a function. Particularly, this is a particular type of function that we call a set function. It's called a set function because the input to our function is a set. Right? These events are sets. So this idea of probability takes in a set and returns a number. So it's a function. Okay, so let's kind of put all this together and state our axioms of probability. So Kolmogorov, when he was working with probability, what he did is he says, well, okay, probability is a function, and so let's state some basic probabilities that probability as a set function should satisfy. And they're properties that we're not going to prove. We're just going to accept them as being self-evidently true. And so let's state our axioms of probability. And these axioms say, assume that for each event A, a probability P of A is defined in such a way that the following 3 properties hold. Okay, so there's 3 axioms of probability. The first 2 are rather simple. The third one is a little bit more complex. The first property says that a probability is always between 0 and 1. That seems rather obvious. That's kind of the way we define probability back in section 1.1. Nothing too unusual there. The second property says that the probability of the sample space equals 1. Now, kind of informally, what this is saying is that if we were to do a random experiment once, we're guaranteed that something's going to happen. Okay? That seems rather obvious. Nothing too mind-boggling there. Now, the third one says that if A intersect B equals the empty set, so in other words, if A and B are disjoint, then the probability of A union B equals the probability of A plus the probability of B. So the probability of the union of disjoint sets is equal to the sum of their probabilities. Now again, that third axiom seems a little more complicated than the other 2. And in the book we give one example to try to motivate why that third axiom is true. But again, we're not going to try to prove that anyway. We're just going to accept this property as being self-evidently true. Okay. Now, what do we do with these axioms? Well, as we mentioned before, we're going to use these axioms to prove results in probability, other simple results in probability. And then we're going to take those simple results and use them to prove more complex results. So whenever we talk about a property of probability and try to prove that property, we're going to start off with these axioms and use them to prove those results. Okay. So your assignment from here is to read section 1.4. And as you're reading through it, keep in mind that these three axioms of probability form the foundations of all the proofs that we do in this section. These three axioms form the foundation of everything that we do in probability, and we're going to use these three axioms to prove all these different results.